This is a dramatic reading of Snarky Puzzle Answers 2, a blog by the Stand-Up Physicist, available at science2.0.com. Now, this blog will contain 4 snarky puzzle questions, their backstories, answers, and discussions. And so the first one came from the April 18th blog, Higgs, we ain't got no Higgs. And here was the snarky puzzle. Factor b squared minus c squared. That should remind you of problems back in high school, maybe junior high, maybe even first grade if you were gals too. Earlier in the post that I did at that time, it was shown how to write a gauge invariant combo of minus e plus b. When the order of operations is flipped, only terms with cross products or the curl would change signs. So do that here. Crash the 2 gauge invariant quaternion 3 vectors to make a quaternion and a Lorentz invariant scalar. And point to the meaning of the resulting 3 vector. The backstory is that I was preparing to give an independent activities period class at MIT. So long as I could find a sponsor, I could ramble on whatever I wished. I made a rather feeble effort to get the physics department there to sponsor me, but they said their plate was too full. Why don't you try the Alumni Association? And boy, were they great. The Alumni Association is used to being nice. And they pointed out that a course like this should be something that freshmen could actually take. Now, an MIT freshman is going to be a top-notch high school student who actually likes math. I worked really, really hard to make sure that I didn't skip any steps, having always hated that phrase, and the rest will be left as an exercise. My motto is that all steps should be small steps. Now, my goal in this class was to show them how to derive the Maxwell equations from the Lagrange density using only small steps. I stayed up really late, lots and lots of nights doing that. But one of the core first steps was at the heart of this sneaky puzzle. And so here's the answer off screen. Yes, yeah, that looks right. Oh, sorry, I should share. Oh, there we go. All right. So take the scalar of this term, plug it into the Euler-Lagrange equations, and out pop Gauss's and Ampere's law. If you don't know how to do that, which believe me is outside of most people's experience, well, then you can kind of search for derive the Maxwell equations and more. Either get the PDF from visualphysics.org or watch the YouTube video. It takes like an hour and a half or something like that to at least appreciate all the details that go into it. So that 3 vector there is known as a Poynting's vector, and it just shows up. On the wiki page, they talk about different people inventing this vector. One of those people being Oliver. I really hate quaternions, Heaviside. There's actually another Lorentz invariant scalar formed only from E and B fields. And in preparing for the lectures, I figured out why E dot B is invariant. What one does is calculate the lengths of that minus E plus B and minus E minus B and subtract them. Now, the lengths of these vectors are actually the same. So the difference will always be 0. And actually, I've been kind of wondering, does anyone out there know why E and B are really orthogonal? You know, I forget why that is the case. I mean, is that the case like only in the vacuum, or is that kind of generally true? I should know that, but hey, I should know everything, but I don't, or I knew it and I forgot it, that sort of thing. Now, what was interesting is why that's useful, this E dot B Lorentz invariant. And if you plug that into the Euler-Lagrange equations, then you get the no monopoles and Faraday's laws. In other words, you get the other two Maxwell equations, there being a collection of 4. And I don't think that's mentioned in Jackson's classical electromagnetism. So it's not as widely known these days. Now, the standard road to b squared minus e squared involves, I think, measurably more work. So one must know the rules of covariant and contravariant for vectors. Then one must struggle to learn the opposite kind of rules for covariant and contravariant for derivatives. Then you must keep track of all these differences while you take a metric and use that in the contraction step. Now, in the end, you get a scalar and you don't get the pointing vector. Now, some will argue that's a good not to have that pointing vector, as it is not really relevant to the calculation at hand. But I prefer a complete story. So if the pointing vector just shows up naturally as part of the calculation, I actually take that as a good sign. On April 26th, we had the sexy standard model symmetries blog. And here was that puzzle, that snarky puzzle at the end. Imagine a space-time wire cube. No, don't. That's just too hard. Think of something simpler. Draw a square in 3 complex planes. Now imagine animating that. Got your picture in your head? Good. Now Google for a 4D wire cube and be honest if your imagination matched reality. Here's the backstory. It's really a classical case of intellectual intimidation. You know, students are told that they will never be able to imagine 4D space. Well, not only is it that true, but it's also not relevant. What we all can watch is a 3 spatial dimensions and time, because we breathe and we just open our eyes and wow, we are in a world that has 3 spatial dimensions and time. You know, so really space-time is ordinary, not extraordinary. I happened to purchase a book. Let's see, where is that book? I had it. Oh, it's right over here. Yes, this book. Andrew J. Hansen, Visualizing Quaternions. You know, I purchased this basically almost as soon as I saw the title. But you know, it started out fun. You know, I mean, he's talking 100% quaternions. You know, so, but I really started getting into deep trouble really pretty early, because he says in here like equations 4.1, 4.2, 4.3, 4.4 are form the foundations of this book. And when I read those, I was like marking them. It's just saying, "Oh my goodness, these don't sound like this. Does not sound like the complete story to me." You know. So I mean, it's not so much that they're wrong, but they're kind of placing constraints that I don't think should be there. You know, the most important and obvious one is that he said he would only work with unit length quaternions. Quaternions that had, a length of uno. And to me, this guy's a computer science guy, not a physics guy. He should be able to deal with animations. And, how big something is just really a measure of how long your video goes. So I thought, well, maybe I should, strike up a conversation with a fellow and say, hey, I think you got some of your basics wrong. And, well, my one effort to reach him via email, got a null result. So you really can't say anything about that. He does have a 4D cube up on YouTube. And it basically looks like a fancy piece of crap to me. I mean, it spins and it morphs and it changes into a ladybug. No. A cube is a cube. There's no morphing. There's no twirling. A cube, a wire cube, is hard right angles. That's all there is to it. And here is what it looks like. So I told a blind guy who emailed me about this animation I had about a spacetime cube. And he corrected me, saying that I had a spacetime wire cube because it is only the wire cube that is mostly empty. Strange to be corrected by a blind man on a visualization, but it happened to me. So, analytic animations are transient. I think that is the hardest part to accept. The 3D wire cube we expect to see blinks into existence and then disappears at times t equals -1 and t equals +1. I should say somebody's pointed out that maybe I'm choosing a very kind of square-faced look at this, that maybe if I turn things in space-time, it won't be as blinky, as it were. And I'm going to go do that experiment, and well, if I find something interesting, I'll include it here. Okay, so I did the experiments, and they were so interesting. I'm going to discuss them here. This first one here is where I do a rotation in 3D space. So it's still got that blinky quality to it of seeing everything all at once and then just watching the points kind of go through space, through time until they get to the other one. What's kind of neat is in the complex plane, because I did rotations in both X and Z, you get this tennis court kind of look. The Y, where I didn't mess with it at all, looks like a solid square. So then the discussions in Science 2.0 led me to say, let's do a Lorentz boost. So this is like speeding up this thing very significantly. And the first thing I did was to do boost along the x-axis, and the x-axis only. And that's the one that's got this kind of slanted, what do we call that? Parallelogram. That's what you call it. And the other ones are tennis courts, but they're kind of tennis courts because time is really changing for that. And you can see in this animation that you have this, instead of having 2 sets of 8, you have 4 sets of 4. And I don't know, I think that's really kind of cool to see that, kind of basically you're getting walls of 4 events happening at 4 different times. So then the question becomes, well, how about a boost along X and along Y? And now you've got 2 parallelogram sort of things. You've got more lines on your tennis court, and you're kind of broken up into more smaller parts. You've got now 8 sets of 2 events each. And this, what it looks like is, it looks like we're drawing this this square now, and we start with kind of like the near far doing the drawing, and then we keep on going till we get to the very last one, and you can see the near far kind of like going away together. So then you say, well, what happens when you do a boost along X, a boost along Y, a boost along Z?
Well, what you expect is that everybody's kind of more independent. And you really start in one corner, and then, soon after, the other one kind of gets going, but there's they're not, perfectly in tune anymore. So that's what happens when you do boosts in X, Y, and Z. You start at one corner, you end at the opposite. I think that's really kind of, and why? Because what is simultaneous in special relativity is relative. It's not absolute. And this boosting of this spacetime cube wire cube shows that point in a kind of a novel way.
But at this angle in spacetime, the majority of the animation is spent transporting the 8 vertices between those 2 moments in time, -1 and +1. The vertices are traveling in time. The problem with the phrase traveling in time is that people associate that with spooky stuff, like traveling backwards in time. Look, we are all traveling forwards in time. Flip through a photo album and you are traveling backwards in time. 1 week, 1 year, a decade. It all depends on how old the photo or video happens to be. My May 3rd blog was entitled Sexy Standard Model Symmetries 2 Experimental Corrections. Here was the Snarky Puzzle. Be a flatlander. Imagine what it looks like if only 2 numbers are varied for the non-zero constant animation. Wear a bow tie to celebrate your correct answer. So the backstory is that I really wanted to find U1 cross SU2 cross SU3 using only quaternions. This is the ultra-conservative part of the ultra-conservative fringe. Say the same thing all the pros are saying. Well, the unit quaternions are sitting in the middle of the standard model. That is the SU2. No debate going on there. Now, I tell people that quaternions really are 3 complex numbers that share the same real. The group U1 is a normalized complex number. So normalizing a quaternion and 3 normalized complex numbers are like kind of guaranteed. So that's cool. So I actually then spent a couple of years trying to reach out to the 8-fold way, the SU3. So here is that animation, and you can see it does in fact look like a bow tie. But I realized that this bow tie is kind of an artifact. It was actually a result of the limited range in input. I chose random numbers between -1 and +1, not minus infinity and plus infinity. So, like calculations, pictures can deceive. What may have a longer term impact, though, is my research, is actually in my research, which is that I may actually give up my goal of trying to get the tensor products of those 3 groups, U1, SU2, and SU3. We know these symmetries must exist in a unified field theory, Lagrangian, so that the weak, the electric, and the strong forces will all be conserved. I mean, that's totally necessary. We've got to have them. But what we don't know is the X in U1 cross SU2 cross SU3, symbolizing the tensor product of these 3 groups. So that certainly is like the most natural assumption to make, but it's still an assumption. As is my way, I'm going to tack my sailboat a different direction, because all I need are the symmetries So therefore, that's all I'm going to use. I mean, it's well known that the group U1 is a subgroup of the group SU2, which is a subgroup of SU3. If one writes a Lagrangian with SU3 symmetry, it necessarily will conserve an SU2 and a U1 charge. It is understandable for people to dismiss such an observation. We prefer a world with separate buckets. This one for electric charge, that one for the 3 weak charges, and let's put the strong charges over there. Because different things deserve different buckets. If EM is a subgroup of the weak force, is a subgroup of the strong force, I don't know, that makes them seem too intimately related. The only relationship the three groups must have is that all are conserved. If one is conserved, well, they all are conserved. And they all are. All for one and one for all, as the Three Musketeers would say. This is the anti-E8 hypothesis, monster minimalism. Finally, on May 10th, I wrote the blog, Gotta Get 16 Gamma Girls. And I think I should let you know I'm actually thinking of changing the title to something like Gotta Get 11 Dirac Gamma Girls and 5 doing an imaginary twist. The reason being that after some discussion happening recently at Science 2.0, I had to finally see some factors of I, and I think it's so important that I probably am going to change the title of the blog. But let me go on anyway to the Snarky Puzzle at the end of that post. At ICC 8, that's the International Clifford Conference, the 8th one, in Campinas, Brazil, I pitched my quaternions plus California ring program to Professor David Hastings of Clifford and geometric algebra fame. Now, being a seasoned vet, this sounded like an old bad dream to his ear. Quaternions are just a bit player, CL02. In the larger C of Clifford algebras, the real numbers are CL00 and a subgroup of quaternions. The complex numbers are CL01 and a subgroup of quaternions. And, the gamma matrices belong to this Clifford algebra CL13, and those can be represented with quaternions. Actually, got to put in my, not really anymore, because we've got to have those factors of I, and those factors of I mean it's not really exactly the same thing. Okay. So in an earlier Snarky Puzzle, I showed how to represent the Lorentz group using real value quaternions. So quaternions are actually are also intimate friends of 4-pi rotations that are needed for spinners. So please list all the important things that quaternions cannot do. All right. So the backstory is that my first international meeting was in Rome, and it was focused only on quaternions in 1999. And I waited in vain for the third one to be now announced. And every 3 years, though, they did have a meeting for Clifford algebras. I decided to go to that 8th International Conference on Clifford Algebras, ICC 8, and their applications to mathematical physics. And if you look in this photo, I am in the second row. How about that? I got to talk for an hour, which is actually triple my time slot. I usually get 10 minutes, 8 minutes. Please be done in 2 minutes and leave. No, not that bad. The big draw, though, was this guy, Professor David Hastings, I guess. The force behind geometric algebra. And he's actually in the 4th row, a night move away from me. One conclusion he had reached is that his new efforts need to have an educational component to them to teach people these deep lessons in geometry he had seen. I'd actually reached a similar position, and it's one of the reasons I make so many of these YouTube videos, and also that command line quaternion animation stuff, because if you can see it, maybe you can understand it in a new way. And ICC 9 is set to happen in July, but due to responsibilities of the family, which fortunately are very cute and talkative, I won't be able to make that trip. So, as I say, as far as the answer is concerned, there is a problem with the question. I say the gamma matrices belong to the Clifford algebra CL13. Well, that's actually true. But can be represented with quaternions? No, can't be done. Something close to them, a few factors of I different, but factors of I matter. But it's still an open question whether that's of interest. I think it is. I think they got it wrong. I got it right. But that will be the subject of further research. All right. Okay. So the answer to this now modified question is that a gravity field theory that can integrate with the other three forces of nature can't really be done just with quaternions. There you need this California ring, in my opinion, to pull off that trick. And let me add just another caveat, and that is that a fellow named Mendel Sachs, actually has done work to mesh quaternions with general relativity. Now, general relativity, as we know, is something that works just on gravity and doesn't know how to play nicely with the other fundamental forces of nature. Okay, so why can't quaternions pull that off? Well, it's because a metric is symmetric, and changes in a metric must be symmetric, and quaternions just cannot do the job, but perhaps this California ring can. Hestenes gave a provoking talk titled Geometry of an Electron Clock. It's actually a revival of an idea of Louis de Broglie. De Broglie. I think that's how they pronounce it right. De Broglie. And even though my life is like really hectic, I decided to watch that hour-long talk again. I was able to travel back in time and space to 2008 in May in Brazil and hear that talk again. And de Broglie viewed the electron as an actual clock. If you plug in the values for an electron, you get its frequency is a little bit less than a zeptosecond. I'm not familiar with those. That's you don't have a zeptosecond clock? Good. That's 10 to the minus 21. Sounds reasonable. But there's actually been experiments to detect that particular clock frequency, and they've actually seen it. But they published it in a de Broglie journal, which, guess what? Nobody frickin' reads, except the other people who are in the de Broglie Institute. You know what I'm saying? So Hestenes is trying to, give it a little bit more exposure. He explains it actually as a rotating electric dipole. And at time 58 minutes, 13 seconds, you can hear me, get out of town, ask the final question about how his work might relate to the Higgs. And he said, well, there's much more work that needs to be done for his model to really be a good contender, that sort of thing. Now, in my gem theory, there are actually all kinds of dipole solution for a fully relativistic field equation. There's so many that I didn't know what to do with a single one of them. Okay? And then I thought, well, you know, if I got an electron here and I got an electron here, what are they going to do? Well, they're going to be torn. They're going to be attracted to each other because of gravity, and they're going to repulse because of electrical their electric field. Okay, the repulsion is going to be way, way bigger, but still, you might be able to view that electron as really being a dipole. It's got two charges. It's got one that attracts, another one of these, and it's got one that repels, another one of these. So it would be really cool if someday in the future I was able to tie those kinds of, that kind of dipole and do a kind of a variation on de Broglie and Hessianese. I mean, that'd be cool. So, anyway, those are the Snarky Puzzle Answers 2. So, thank you very much.